In this lecture, we'll first talk about the instantaneous center of rotation. We call it ICR for short. And then we'll start driving the kinematic equations of wheeled robots. ICR is a mathematical concept. If we consider pure rolling of wheels with no side skidding, each wheel has a zero motion line through its horizontal axis perpendicular to the wheel plane. At any moment, wheel motion through this line must be zero. So the wheel must be moving along some circle of radius r such that the center of the circle is on the zero motion line. The center point is called the instantaneous center of rotation of the wheel. At each instant, the motion of the robot chassis can also be viewed as an instantaneous rotation around an ICR whose position with respect to the chassis can be time varying. At any time, the ICR of the robot chassis is the intersection of all zero motion lines from the wheels. Hence, at each time instant, the velocity vector of any point of the chassis is orthogonal to the straight line joining the point and the ICR. The ICR changes over time as a function of individual wheel velocities and in particular of their relative difference. In the diff drive robot, VR and VL represent the velocity of the center of the right and left wheels respectively. V represent the velocity of the reference point, which is on the chassis, and here it is placed on the center of two wheel axle. In this case, the lines of zero side motion coincide, and therefore the ICR can be located at any point on the line of zero motion. At any time, the reference point moves along a circumference of radius r plus d. You can see r here, and since the axial length is 2d, so the diameter of this circle will be r plus d, and the center is located on ICR. Now let's see what instantaneous center of curvature is and how it differs from ICR. The ICR is defined by the velocity vector of 2 points at one instant. In contrast, the ICC is defined by the velocity vector trace of 1 point through time. Suppose that the velocity of the center point of a diff drive robot at time t is denoted by v of t, and this point moves on a trajectory for the duration dt. Here it is assumed that dt is very small and tends to be 0. The velocity of the reference point at time t plus dt is equal to v of t plus dt. ICC is placed at the intersection of the perpendicular lines of these velocity vectors. Note that the velocity vector of the reference point is always tangent to the trajectory. It is also important to note that to note the fact that the velocity of the reference point for the diff drive robot is always in the same direction as the velocity of the center of the wheels. This is not the case in all wheeled robots, so the ICR and ICC can be placed at different points. It's worth noting that here there is a relation between alpha and theta. Theta is equal to theta is equal to pi over 2 minus alpha. We will use this in the next slides. Suppose in the case of diff drive robot, the velocity of the right wheel is 0 and the velocity of the left wheel is constant k. In this case, the ICR and the ICC location will be the same, and they will not change over time. A clockwise rotation about the right wheel will be performed in this case. If the velocity of the right wheel is negative k, and the velocity of the left wheel is positive k, the robot will perform a rotation about the midpoint, and we call this in-place rotation. In this case, the ICR and ICC will be the same and will not change over time. There is an interesting relationship between ICR and degree of mobility. If for a robot we are not able to place the ICR in a place, for example in this robot, its mobility is 0. In this case, no motion is possible without a slippage. If at each instant only one unique point is specified for ICR, for example, in the case of car-like robot, its degree of mobility is 1, and if there is a line of ICRs, then the degree of mobility is 2. As you know, depending on the velocity of the left and right wheels, the ICR of this robot may be located at any point on the line, and in this case, if you can put ICR everywhere at any position, so the degree of mobility is 3. Now we'll move on to kinematics. I mean the kinematic modeling of wheeled robots. As you know, the study of kinematics is often referred to as the geometry of motion. Kinematics refers to the study of motion without taking into consideration the forces and torques that cause it. It's based on geometric relations, positions, velocities, and accelerations. Forward kinematics refers to the use of kinematic equations to determine or predict the final configuration or pose of a robot based on the specification of the values for the actions which are done by wheels. In inverse kinematics, given the desired final configuration or pose of the robot, we obtain the value of the actions, the value of the actions that allow us to achieve it by the robot. In the problem of direct kinematics of a manipulator, the values of the joint variables, which are Q1, Q2, Q3, and Q4, for example, in this robot, are known, and the pose of the robot's end effector, X, Y, and theta, are obtained with the help of kinematic equations. So in the forward kinematics, Q1, Q2, Q3, and Q4 are known, and we should obtain the pose of the end effector. In inverse kinematics, given the desired pose of the end effector, x, y, and theta, the values for the joint variables are determined. As you know, the inverse kinematic problem may have several solutions and or no solution at all. In the case of wheeled robots, forward and inverse kinematics are slightly different. Due to the existence of non-holonomic constraints, in the forward kinematics and inverse kinematics of these robots, velocities are raised. In these robots, we have action and pose. In the case of the diff drive robot, as you can see in the slide, the right and left wheel velocities constitute the actions. VL and VR are the actions, with these actions, the robot will speed up and reach a certain pose. Pose is defined by x and y and theta. One point of the chassis, for example, the center of the axle can be considered, and the pose of the robot can be defined based on that. In forward kinematics, the action is known and the pose is unknown. In inverse kinematics, the pose is known and the actions are unknown. And we should relate the pose and action with some equations. Given the geometric parameters, the initial pose and velocity and assigned action, VL and VR, a forward kinematic model aims to predict the robot's rate of pose change in the global reference frame or world coordinate. You can see the world coordinate here. So first, we obtain a relation between the actions and the rate of pose change in global reference frame. The rate of pose change here is denoted by xi dot, and g is a function that relates actions with rate of pose change. Once this relation integrated over time using the initial conditions, the new robot pose can be then computed or predicted. And here you can see that xi equals fk of d, theta, vl, and vr, in which d and theta are some parameter. D is actually the axle, the half of axle length, and theta is the heading angle. And here you can see the relation between actions and the final pose. Therefore, the kinematics of the robot is determined based on F and G, I mean Fk and G, and we will look for them in the kinematic modeling of wheeled mobile robots. In kinematic modeling, some simplifying assumptions are considered. Here are 5 important assumptions. Assumption 1, the wheeled mobile robot does not contain flexible parts. We make this assumption to apply rigid body mechanics to kinematic modeling. Assumption number 2, all steering axes are perpendicular to the surface of travel. By training the steering links to be perpendicular to the surface of travel, we reduce all motions to a plane. We thus constrain all component motions to a rotation about the normal to the surface of travel and to translation in a plane parallel to the surface. Assumption number 3, the wheeled mobile robot moves on a planar surface. This assumption neglects irregularities in the actual surface on which a wheeled mobile robot travels. Assumption number 4, the translational friction at the point of contact between a wheel and the surface of travel is large enough to so that no translational slip may occur. This assumption ensures the applicability of the theoretical kinematic properties of a wheel in rolling contact with the two translational degrees of freedoms. This assumption is realistic for dry surfaces as demonstrated by the success of braking mechanism on automobiles. Assumption number 5, the rotational friction at the point of contact between a wheel and the surface of travel is small enough to so that rotational slip may occur. The wheels must rotate, slip about their points of contact to navigate a churn. Since wheeled mobile robots also rely on rotational wheel slips, we include this assumption. Okay, let's start the kinematic modeling of wheeled robots by starting with a simple robot. Here you can see a simple robot with an active wheel. It can only move in the X direction. So here, what is the pose and action? It's clear that the pose is determined just by X, and the velocity of the wheel, shown as V, in the X direction is the only action in this robot. So V is the action and X is the pose. If we apply the action for t seconds by simply using the definition of velocity, which is the time derivation of position, we can write x dot equals v, or dx over dt equals v, and then by integrating this relation from 0 to t, the displacement is obtained. Note that in the case that v is constant, the displacement will be v times t, and the displacement delta x is equal by definition to the new pose minus initial pose. Therefore, finally, the pose will be equal to x0 plus v times t. So the function f(k) that represents the forward kinematic model is obtained. It should be noted that f(k) is dependent on x0 action, which is denoted by v, and movement time. So given the initial position and action and the time duration, we can obtain the final pose of the robot. We can also represent the kinematic model based on wheel angular velocity. If one applies constant angular velocity psi dot in rotations per second for t seconds, and r denotes the radius of the wheel, the forward kinematic model can be finally written as x equals x0 plus the multiplication of 2 pi r psi dot t, and FFK is obtained. Note that psi dot, in this case, is given in rotations per second, not in radian per second. So we just replace V with 2 pi r psi dot in this relation to obtain the kinematic model. To obtain inverse kinematic equations, we can use simple relations. The displacement delta x is equal to t times v, in which v denotes the constant velocity during the time duration that we represent it by t. So we can write v equals x minus x0 over time, over t. This equation shows the inverse kinematic model. So if ik is a mapping that takes a pose as an input and specifies action as output. You can see that here. It takes x as an input and specifies action as the output. In other words, given the pose and initial pose of the robot as well as the time, we can obtain from this equation the required action, which is represented by v. We can also obtain the inverse kinematic based on wheel angular velocity. This is very simple, and you can see its relations on the right side of the slide. As seen, the solution of inverse kinematics for this simple robot is unique. Generally, there is a unique solution for the forward and inverse kinematics of this robot. Now consider the previous robot in two-dimensional plane. Here, theta is fixed, the heading angle is fixed, x and y denote pose, and as before, v is the action. So pose and actions are determined. For the forward kinematics of this robot, we can simply write delta x equals integral from 0 to t of v cosine of theta times dt. And if we consider a constant v, we can solve this integral and obtain t times v times cosine of theta for x. And we can also write delta y equals t times v times sine of theta. By integrating the equations of the previous slide, the direct kinematic equations can be obtained in this way. X equals x0 plus t times v times cosine of theta. Y equals y0 plus t times v times sine of theta. Given the initial pose of the robot, x0 and y0, theta and time, time duration, as well as the action v, we can obtain from this equation the final pose of the robot. This is the forward kinematic model. With a simple algebraic manipulation, the inverse kinematic equations are easily obtained from forward kinematic equations. Here you can see the inverse kinematic equations. As seen, given the pose and initial pose of the robot, as well as the time duration and theta, we can obtain from these equations the required actions, which is represented by V. It can be seen that the inverse model does not have a solution in some situations. For example, if theta equals pi over 2, it should be noted that in this case, since theta is constant, there is a linear relationship between x and y. Therefore, they are dependent on each other, and if they are inserted in these equations based on this dependence, only one v is obtained. In other words, inverse kinematic does not work for any arbitrary x and y in the plane, and this mobile can just move on lines. In the case of the diff drive robot, both left and right wheels are active. So as seen before, the actions are VR and VL. Inactive wheels also maybe exist. The pose is determined by x, y, and theta. Next, we want to derive the kinematic equations of this robot. As seen previously, we can obtain the ICC based on two different poses of the robot. Here, B represents the distance of the center of the right wheel from the ICC, and as before, the length of the axle is equal to 2D. Suppose diff drive moves in a short time, we can assume that the wheels go in circles. The circumference of the circle on which the left wheel moves is denoted by CL, and it's equal to 2 pi times B plus 2 times D. And the circumference of the circle on which the right wheel moves is denoted by CR, and it is equal to 2 pi times B. Distance traveled around the circle for the left wheel, dl, corresponds to alpha radians in a portion of the circumference of the circle. This ratio is equal to alpha over 2 pi. If we substitute the CL from the previous slide, we will have this relation. Then we can solve this equation for alpha. So we have alpha equals dl over b plus 2d. We can do the same for the right wheel, and we can solve the equation to get b. Using these two red equations, we can write that alpha is equal to dl minus dr over 2d. According to the figure, theta is equal to the pi over 2 minus alpha. And we know that omega delta equals d theta over dt. So it will be equal to negative d alpha over dt, the time derivation of alpha. Anyway, finally, using green relations, we can write omega equals v r minus vl over 2d. So we can obtain a relation for omega. Furthermore, by using velocity relations for a rigid body, it can be easily seen that Vt equals Vr minus, Vr plus Vl over 2. I should correct this one. Yeah. So, so far we have seen from the kinematics of diff drive robot that omega equals VR minus VL over 2D. If VL is equal to VR, omega will be 0. And in this case, the mobile robot will move on a straight line. It can also be seen that from this relation, for a certain difference between VL and VR, the smaller value of D leads to a higher angular velocity for the robot. So the dexterity will be enhanced in this case. For a diff drive robot, the velocity of the reference point located at the center of the axle is also obtained with this relation. I should also correct this one. Okay. The kinematic equations of the robot can be finally written as seen in these equations. We have an inertial reference frame, inertial coordinate system, and a body coordinate system is also attached on the chassis of the robot, which in this case is located on the reference point of the robot, which is between the axles. We denote the body coordinate with XR and YR. In these equations, the pose of the robot is expressed in the inertial coordinate system. Vt is the velocity of the reference point, and it is along the heading angle. The angle of Vt with the x-axis of the world coordinate is equal to theta. Since omega of t and v of t in these equations are generally functions of time, so these integrals cannot be solved analytically. However, if we assume that the velocities and angular velocity are constant, and for the case that theta 0 is equal to 0, these integrals can be solved. You can see the solution in this case here. When the velocities and angular velocity is constant, we can obtain these relations. As seen in these relations, given the action and the initial pose, we can simply obtain the pose of the robot, the final pose of the robot. Now, let's talk about the inverse kinematic of the diff drive robot. The related question is, how should be action to reach a given configuration or pose? As you know, the non-holonomic constraint imposes limitation on instantly establishing of a position for this robot. For example, this robot cannot move directly sideways in this way. Mathematically, according to the kinematic equations, we can't just specify any pose and compute a linear and angular velocity to get there. In these equations, you can see this fact. There is also no solution even with the constant velocities in some cases. For example, for sideways motion. However, we know that it's possible to reach anywhere on the plane by some maneuvers similar to parallel parking. Let's rewrite the kinematic equations again, and this time we replace V with its equivalent, which is VR plus VL over 2. And we also replace omega with VR minus VL over 2D. Regarding these equations, if VL equals negative VR and equals constant V, then the robot rotates in place, and the equation becomes in this form. So in these equations, the VR plus VL will be 0. So we can. So the pose of the robot will be constant, and just the orientation of the robot will be changed. We can simply obtain the pose of the robot with this relation, and also with algebraic manipulation, we can obtain also the action in this form. So for a in-place rotation, the actions equals to this to d times theta minus theta 0 over t. For the special case in which VL equals VR equals constant V, robot will move in a straight line with constant velocity, and these equations can be integrated to obtain the pose of the robot. This motivates a strategy of moving on the robot in a straight line, then rotating for a turn in place, and then moving straight again as a navigation strategy. So with this strategy, we can move the robot in sideways. With some maneuvers, we can reach a point that is located on sideways of the wheel. In fact, this is a path planning issue, and we will talk about this more in the path planning section. Okay, in the next lecture, we will introduce the derivation of kinematic equations from a different perspective, and then we will model some other wheeled mobile robots.